Let's return to our discussion of interference in light waves by examining two phenomena. One of them had a significant impact in the development of our understanding of the universe, and the other has a pretty significant impact in our day-to-day lives, even if you don't really notice it. The first thing we're going to talk about is the Mattson interferometer. On the screen, you can see on the left a picture of such a thermometer. It involves a laser, as you can see with the white object in the upper center, and you can see the laser beam and the laser beam. You can see a small red spot right in the center of this square-looking shape. This is part of the Mattson interferometer. The interferometer works in a way in which it separates this incoming beam into two separate beams, and then recombines those beams in a way that causes them to interfere with each other. And when they interfere with each other, you see through an eyepiece, the image like one on the right. Now, how does it work, and why did it come into formation in the first place? In the 19th century, there was some discussion about the nature of light, as we've mentioned before, and it was realized that light was wave-like. It had been confirmed experimentally at the start of the 19th century, and then James Clerk Maxwell developed the theory behind it to show that it is wave-like. But that led to a question, because any wave that existed was known to travel through a medium. We have a wave in water, sound is a wave in air, seismic waves are waves in ground. So if electromagnetic waves are waves, they require a medium. So what medium would that be? And they decided to call this medium ether. The inspiration for this name comes from the ancient Greek philosopher Aristotle, who in his natural philosophy said there were four basic elements: air, earth, fire, and water. And then there was a fifth element, a quintessential element that was found in the heavens, and Aristotle called this ether. On the screen at the bottom, you see the five so-called regular solids that represented in Aristotle's philosophy these five different elements. The third one, the dodecahedron, was the regular solid that was representing ether. Now, the point of having a medium in which waves travel is that if you're the source or the observer, your speed with respect to the medium matters. So if this is true for sound waves, it should be true for light waves. And this is what Mattson and Worley tried to investigate. If the Earth is moving through this heavenly ether, then something on the Earth that is stationary with respect to the Earth ought to be moving relative to the ether. And so as a source, there ought to be some sort of effect moving in one direction or the other direction. You can see in the image, if the source is this blue spot, as it moves to the right, the wavelengths in front of it are compressed and the wavelengths behind it are stretched out. So this was the expectation for light. This is why they built the Mattson interferometer. This very subtle measurement, because we're talking about something on the order of the wavelength of light. This very subtle measurement is necessary in order to be able to determine if there is a difference in the wavelength moving in one direction or the other direction. We saw a picture at the start of these slides. Let's understand a little bit about how it works. The laser, or whatever the coherent light source is on the far left, and it emits a beam. And that beam reaches a half-silvered mirror, and half of the ray is going to reflect, and half of the ray is going to pass through. And these two rays then reach mirrors. So you'll see that about half the intensity is reaching the mirror on the right, and about half the intensity is reaching the mirror on the bottom. And then these rays, of course, reflect and return back to this half-silvered mirror. Of course, upon encountering this half-silvered mirror, some of these rays will pass through the half-silvered mirror and travel to the left, but a portion of the rays will reflect off of that silver mirror and move upwards. So we get a mixture. The ray reflecting off of the lower mirror passes through the half-silvered mirror. The ray reflecting off of the mirror to the right reflects off of the half-silvered mirror, and those two rays are allowed to interfere with each other at the detector. And the detector could be your eye. We don't care about those rays, but those rays will overlap each other. We use a lens to slightly focus them together to have them be in the same place at the same time, and they will interfere with each other. The interference pattern looks very similar to what we showed in the very first slide. If you view the interference through this eyepiece, you're going to get this set of ripples here. And it appears static. It's not like it's spreading outwards. If you're not touching any of the apparatus, the image is just a constant series of concentric rings. But you might have noticed that in the schematic of the Michelson interferometer, the mirrors were labeled as movable. So the mirrors are represented in the actual interferometer in the picture here. They can move back and forth. And in moving back and forth, that means that the path length traveled by each ray of light is adjustable. And as you adjust the path length, that means that the path length difference between the two rays is changing. And if you change the path length difference, you change the phase shift. And if you change the phase shift, you change the relative intensity of the net wave reaching you. As you move a mirror in one direction or another and you look through the eyepiece, it looks like ripples spreading outwards, and there's a constant source of new ripples coming up from the center. Or if it's the mirror is moved in the other direction, it looks like ripples that are collapsing in on themselves at the center and then disappearing. It is possible to move a mirror and count the number of times you see a ripple collapse inwards or spread outwards. And how that is affected, as stated before, is if you can adjust the location of a mirror. If you adjust the location of one of these mirrors by a distance d, the path length difference changes by 2d because the ray has to go towards the mirror and then reflect back off of it. By having these two mirrors perpendicular to each other, you will ensure that they are not traveling in the same direction with respect to the ether through which these mirrors are supposedly moving. By reflecting off of these mirrors, as we've discussed before, these mirrors effectively serve as sources of light. So, if these mirrors are moving at different velocities with respect to the ether, then the wavelength of one of those rays is going to be slightly different than the wavelength of the other one of those rays. And if that wavelength is slightly different, it's going to show up in the eyepiece. You can measure the wavelength, you can measure the interference pattern, and if there's a deviation in the interference pattern, you'll see it. To put some math to this, let's say L1 is the distance traveled by the first ray, whichever one you want to call the first ray. L2 is the distance traveled by the second ray, whatever you want to call the second ray. Lambda 1 is the corresponding wavelength of the first source, and lambda 2 is the corresponding wavelength of the second source. We don't assume lambda 1 equals lambda 2 because these rays are traveling at different angles with respect to the hypothetical ether. And so, as we discussed before, each of those wavelengths will be slightly changed from its base value if they are affected by the ether. The number of wavelengths traveled along path 1 is n1. That's equal to the path length divided by the wavelength. And of course, the number of wavelengths traveled along path 2 is n2. And if n1 minus n2, if that absolute value is equal to an integer, when you look through the eyepiece, you will see a bright spot at the center. As you adjust the mirror, the path length starts changing. Now, N1 and N2 are not necessarily integers. And as you smoothly adjust the path length of one of the mirrors, you will smoothly move N1 away from an integer. And so instead of being equal to 50, it might then be 50.1, 50.2, 50.3, smoothly going through all the numbers, not just integer numbers. So K could be any number, but it's when K is an integer that we have a bright peak in the center of the interference pattern. As you move one of these rays at distance d, the path length changes by 2d. So in a Michelson interferometer, what you do is you start with the two mirrors in a location where you see a peak at the center of the eyepiece. And then you adjust one of the mirrors, and you get this ripple that spreads outwards or collapses inwards. And when you adjust it the distance to see the ensuing bright spot in the center, you've gone through the equivalent of one full wavelength. So playing around with it, you can say that the value of that wavelength, lambda 1, is equal to twice the distance that you've moved the mirror. However, to make sure that human error is minimized, instead of moving the mirror through just one wavelength, it's typically moved through many dozens of wavelengths. And you've got to be looking through the eyepiece and carefully counting the number of ripples that spread outwards or collapse inwards as you slowly adjust the mirror. So eventually you might adjust the mirror a total distance of capital D, and you might count a total number of capital M ripples in the pattern. Both of those quantities being measured, you do 2 times capital D divided by M, the number of ripples, and you have a very good estimate of the wavelength along the first path. Let's consider light with a wavelength of 632 nanometers, and if we adjust one of the mirrors at distance of 0.173 millimeters, how many full transitions would we see? How many ripples or bright spots at the center do we see? Well, the distance in meters is 0.000173. 2 times 0.000173 divided by the wavelength should be equal to the number of ripples that we see. And running through this calculation, I get 547.5. So capital M is many hundreds. We've moved it less than 0.2 of a millimeter, and yet we have hundreds of ripples blossoming outwards from the center. So that means that the wavelength is pretty small. Pretty small by any standard that we consider small. 1/10 of a millimeter by our standard is pretty small. But on the scale of the wavelength of light, that's actually a pretty big distance. Now, Mattson and Morley managed to accomplish this technological feat in the 1880s. And what they found was no matter what they did, no matter what the orientation of the interferometer was, and they did it for half a year because they wanted to make, in case the ether had some sort of flow to it or something, they did it pretty much every day for half a year as the Earth orbited the sun. So they had the Earth moving in one direction as the Earth rotated about the sun in its orbit, and then they had the Earth moving in the opposite direction and every day in between. And no matter how the Earth was moving with respect to this hypothetical ether, there was no impact on the wavelength. And lambda 1 was always equal to lambda 2, no matter what the orientation of the interferometer was. Which meant that there didn't seem to be any impact of the ether on these light rays. In fact, the conclusion was that the speed of light was not impacted by the ether at all, unlike, say, the speed of sound, which can be impacted by conditions in the air. Looks like the ether does nothing. If the ether does nothing, why even talk about it? It was thinking like this that led Albert Einstein down the road to his celebrated theory of relativity. But that's going to be something for another lecture. But the Michelson-Morley experiment was foundational in the development of our understanding of the universe, because relativity is foundational to our understanding of the universe. Now, just a quick little conceptual question. Suppose we let both mirrors in the interferometer move a distance d during the same time at always the same speed. What would happen to the interference pattern that you view in the eyepiece? Is it nothing? Would the pattern oscillate back and forth between creating new patterns or ripples and then collapsing ripples? Would we only see new ripples or fringes be created, or would we only see fringes or ripples be removed? Now, the next thing I want to discuss is thin films. And this is the phenomenon that we see in our everyday lives. We literally see it in our everyday lives. If you're looking at a person wearing a pair of prescription glasses, you are looking at a person who is taking advantage of the technology of thin film interference. The picture on the left is kind of an oil slick, which is an example of thin film interference. The picture on the right is a picture of a woman wearing a pair of glasses that do not have a thin film and a pair of glasses that do have a thin film. And you see that without the thin film, the glasses reflect a lot of the light falling on them, and you get kind of this Little Earth and Annie effect. And I know that's a dated reference, but some of you might get it. Whereas if you have the thin film on the right, the amount of light that is reflected, it's not zero, but it is much less. Thin films allow for the amount of light reflected off the glasses to be fairly minimal, which means that there's actually more light reaching the eyes. How does thin film interference work? We have light traveling in an initial medium. It then encounters the thin film that lays over a surface, and then that surface itself has its own index of refraction. So N1 is probably like the index of refraction of air, probably. N2 is the index of refraction of the thin film. N3 is the index of refraction on the other side of the thin film. If you're wearing a pair of glasses, N3 is for glass. On the other hand, if it's a soap bubble, then N3 would also be that for air. We're only going to consider light that is coming straight into the thin film itself, light that's coming in straight on. And what's really happening is what you see in red. But what's happening in red, everything is happening along a straight line, and it gets confusing. So in order to understand what's happening, we also have the arrows in black that mimic the red, but they're not going to be collinear. So the red is what's really happening. The black allows you to see what's happening. So we have the incoming ray that's coming in perpendicularly to the boundary. At the boundary, some of the ray refracts into the thin film, and some of the light reflects at the surface of the thin film and remains in the original medium. Then we have the ray, marked 1, that reaches the boundary with the third medium. And at that boundary, some of the light refracts into the third medium, and some of the light reflects back into and remains within the thin film. And then that ray marked 4 re-encounters the boundary between the first medium and the thin film. And at that boundary, some of that light reflects and remains in the thin film, but some of that light refracts back into the original medium. This process technically continues on and on and on, but the intensity of the light that remains within the film diminishes with each reflection and refraction. So the primary interference is happening between rays 2 and 6. So these two rays right here, or these two rays as you see them actually overlapping in red, are the rays that are interfering with each other. The interference has two possible sources. The phase shift between the two rays, there could be a contribution from reflection. When a ray reflects off of a surface, there is a chance that the reflected ray is exactly out of sync with the incoming ray. That means that the phase shift, just due to reflection, might be introducing pi radians. Ray 2 is the result of reflection between N1 and N2. Ray 6 has in its history a parent ray that is the result of reflection off of media 2 and 3. So both of them have reflections in their ancestries. So it is possible for none or one or both of those reflections to introduce this half-wavelength phase shift. How do we know when this half-wavelength phase shift occurs? It occurs when the refracted ray, the ray that enters the second medium, has a slower speed. So in other words, if the new index of refraction is higher than the original index of refraction, then the reflected ray is going to be offset by half a wavelength. It's going to be offset by pi radians. So we need to introduce this half wavelength phase shift when N2 is greater than N1. That means that ray 2 is going to have that half wavelength phase shift. But remember that ray 6, in its ancestry, there's a reflection. So if N3 is greater than N2, then ray 6 would have this half wavelength phase shift introduced into it. Now, if both are true, a half wavelength phase shift in ray 2 and a half wavelength phase shift in ray 6's ancestry, the effects cancel out, and we don't have to worry about it. But if one of them has a half wavelength phase shift and the other doesn't, we have to worry about it. So that's something to keep in mind. Another thing to keep in mind is simply the path length difference in ray 6's ancestry compared to ray 2. Ray 2 is the immediate reflection off of the first boundary. Ray 6 had an ancestor ray that traveled from the first boundary to the second boundary and then back again from the second boundary to the first boundary. So the total distance traveled by an ancestor ray to ray 6 is twice the thickness of the film. How many wavelengths that is depends upon the wavelength within the thin film. And recall that the wavelength in a medium is equal to the wavelength in vacuum divided by the index of refraction. So the number of extra wavelengths traveled in the thin film by the ancestor of ray 6 is 2 times n times t over lambda naught, where lambda naught is the vacuum wavelength. If we have constructive interference, then this extra number of wavelengths, that includes both due to thickness and due to the possible phase shift upon reflection, needs to be equal to an integer. And if we want destructive interference, we need that combination to be equal to an integer plus a half. It's entirely possible it's not equal to an integer or an integer plus a half, but somewhere in between. That means that it's not entirely at constructive interference or destructive interference. But constructive interference, when you look at a thin film, those are the wavelengths that show up most brightly. The phase shift means that we have to multiply these sides by 2 pi. And like I said, we can't forget that reflection effect. So here's our equation, and it's actually a set of equations, one for constructive interference, one for destructive interference, and then we have to explain what this term phi reflection is. But if we want constructive interference, this expression on the left, 2 pi plus 2 times n2, which is the index of refraction of the film, times t, which is the index of refraction of the film, divided by lambda, which is the vacuum wavelength, plus phi reflection equals 2m pi. And for destructive interference, we can set it equal to 2n plus 1 times pi. Phi reflection is the same for both constructive interference and destructive interference, and it depends upon the relative relationships between n1 and n2 and n3. And you can see the conditions when phi reflection equals pi and when phi reflection equals 0. Let's apply this to an example. Let's say we have normally incident light on a film that is 0.930 microns thick. It has an index of refraction of 1.41, and the film is laying over glass with an index of refraction of 1.58. And we want the visible wavelengths that are most strongly reflected and the visible wavelengths that are most strongly absorbed, which basically means undergoes destructive interference. N1 is probably air. Didn't say so, but that's probably the case. We'll say N1 is air. N2, the film is 1.41. N3, the glass is 1.58. Under those conditions, phi reflection equals 0. So, if we want to look at constructive interference, since phi reflection is equal to 0, lambda is going to be equal to, after a little bit of algebra, 2 times n2 times t divided by m, where m is an integer. We know what n2 is. We know what t is. We don't know what m is, but I can at least express my wavelength as a number divided by m. Now, m is an integer. It can be as low as 1, and it can be as high as whatever. Let's start playing around with different values of m. If I have m equals 1, well, I have a wavelength of 2.62 times 10 to the negative 6 meters, and that's in the infrared part of the spectrum. If I have m equals 2, if I have m equals 3, I'm still in the infrared part of the spectrum. But if I have n equals 4, I get 6.56 times 10 to the negative 7 meters, and that's red. N equals 5 gives me 5.27 times 10 to the negative 7 meters, and that's green. N equals 6 gives me 4.37 times 10 to the negative 7 meters, and that's violet. Once I get higher than 6, I'm down to 3.75 times 10 to the negative 7 meters, and that's sneaking into the ultraviolet region. And larger values of m lead to smaller wavelengths, so we are now past the visible part of the spectrum. So the rays that would be most strongly reflected are red and green and violet. Now, if I was looking overhead, I wouldn't see a red ray and a green ray and a violet ray. I would see a mixture of all three colors, but those would be the three colors making up the combination that I see. As for destructive interference, again, phi reflection is still equal to 0, but now our expression for lambda is a little bit more annoying. It's 4 pi times n2 times t all over 2m plus 1 times pi. About the only good thing is that the pi in the numerator cancels out the pi in the denominator. But aside from that, it's just flat out a bit more homely. 4 times the index of refraction, 1.41, times the thickness, 0.930 times 10 to the negative 6 meters, divided by 2m plus 1. And when I combine the numbers, I get this expression for lambda equal to 5.25 times 10 to the negative 6, divided by 2m plus 1. And then we start playing the same game. M equals 1, infrared. M equals 2, infrared. M equals 3, infrared. M equals 4 gives us a wavelength that's kind of in the yellow or green part. M equals 5 gives us a blue wavelength. And M equals 6 gives us a just barely visible violet wavelength. So now we know the colors that are constructively interfering and the colors that are destructively interfering. And what we would see is simply the net effect. We don't see the separate colors. We see them blend together to create whatever the ultimate color is for this combination. When you look at a thin film, though, you're probably not looking at it from overhead. Probably looking at it from an angle, and you'll see a shimmery spectrum of colors. Now, that shimmery spectrum of colors results from the fact that the light is not normally incident. And so the light that is reflecting off of it is entering the thin film at ever so slightly different angles relative to each other before meeting up with each other and interfering in your eyes. When I have a single ray coming in, you'll see that the two rays that remain in N1 can't interfere with each other. But there's typically a whole sequence of rays that are coming in, and so there's probably another ray parallel to the first ray that's also coming in, and its reflection can interfere with one of the reflected rays from the first ray. And so these two rays can interfere with each other. And these result in their own particular wavelengths of constructive interference and destructive interference. And what wavelengths result depend upon the incoming angle. And even a slight change in the incoming angle can result in a noticeably different color in the constructive interference. A very slight angle, to really do it, you have to use Snell's law. And Snell's law basically says that instead of 2t being the extra distance traveled, the extra distance is actually 2t divided by cosine theta 2. Frankly, I'm not going to get into that anymore, but it's the fact that theta 2 varies results in a change in the extra distance traveled. The extra distance traveled results in slightly different wavelengths that yield constructive interference or destructive interference, is what's responsible for the shimmery nature of, say, an oil slick after a rainy day in a parking lot. That's all I'm going to say. Take care. Bye-bye.